Welcome everyone. Thank you for joining us today. So we're going to be going through in our presentation looking at automation using a Truss bridge model example and using specifically the PythonParts application. So for presenters, we have myself. My name is Joe Brenner. I am the Regional Technical Manager for BIM for Bridges for Michael Baker International. And I'm charged with developing and implementing technology and refining workflows both for our clients and internally within our organization. I also have with me today Hanjin, and he is listed first here on the slide for a reason. He's the one that makes this all work. He is a senior bridge engineer with Michael Baker International, but also has an extensive background and experience with software development, specifically in bridge analysis software, and even more particularly now focused on BIM for Bridges applications. So for today, we're going to be looking at first kind of going through a little bit of background and where we got to, how we view modeling automation. Then we'll step through a little bit and give you a little bit more information on the example project that I mentioned on that bridge truss model. Then I'm going to turn it over to Hanjin to go through a demonstration within PythonParts and showing some of the tasks that we did automate through this process. He's also going to go through some additional resources, particularly for coding for those that may not have that background. And then finally, we'll discuss some of the specific model outputs and benefits we got out of this particular application and process. So in terms of automation and what we mean when we discuss this, I really like this slide, and it's very simple for me. But think about any application we use, even specifically spreadsheet calculations, right? So we have inputs, could be specific geometry or different parameters there that we're inputting, and it goes into a function cell, could be mathematical, addition, subtraction, could also be looking at conditional if-then type statements, and then through that function, we get outputs from that. Okay, it could be one or many different outputs depending on that. So that in its simplest form is what we're talking about automation. And if you think about it, that is a form of automation. So now looking at this where we start introducing multiple functions, either in series or parallel, now we're able to do much more, right? So we still have our inputs, but now we're able to have the program make certain decisions based on criteria. Okay. And work through those functions based on those answers. Right? Now, this obviously is much more powerful. It also becomes much more complex, right? Which is when we start to need to introduce scripting and coding in order to kind of pull this off now in a larger scale beyond our simple spreadsheet example from inputs to function to outputs. So now that we've introduced what we mean by automation, what are our goals with this? What are we trying to accomplish? So I have it up on the screen here, right? Improve quality, improve effectiveness, and improve efficiency. So not exactly the most shocking statement, not exactly a mic drop moment here, right? I mean, it's what we're trying to do with everything we do, every process, right? So how do we specifically do that using automation? So first, we want to remove repeatable tasks. A simple example of this is automating sheet borders on our plans, automating sheet numbers that go within those sheet borders. So that's a good example, one thing we're trying to do. The next is looking at removing tedious tasks. This is why we do a lot of work to automate reinforcement schedules, for example. Very tedious, very time consuming, but also looking at quality, also prone to errors, right? Human errors. And then finally, we want to take advantage of available data. One of my biggest pet peeves is when we do tasks in one area which have information which 80–90% of that information can be used for another task, and we just throw it away and we start over on this other task. Again, one of my biggest pet peeves, things that we need to take advantage of that available data and use automation and be able to pull that data into these other tasks. So we're going to show you how we use and how we've done that, these three things within our sample example project here. So in this situation, we have a major river crossing here. We're in preliminary engineering, looking at multiple alternatives, and one of them is a truss. So here you can see just kind of a rendering here. We'll get into some of the outputs here in a few slides. But you get an idea of scale with some of the barges and the trucks on the bridge here. So obviously, again, in preliminary engineering, we want to sort through alternatives, looking at things like quantities for cost estimates, preliminary analysis, sizing members, and looking at specifically, again, with this type of structure, major river crossing, a lot of public involvement, environmental concerns, and in this particular situation, barge traffic. So being able to have these images to be able to work with our public and other stakeholders within the project. So when I came onto this project, they already had preliminary analysis completed in a structural analysis this program, right? So all of nodes, elements, sections, materials have all been defined, at least in the preliminary engineering phase. So as we said, one of the things that we look at trying to do with automation is be able to take that information that's already available and use it for other purposes, right? So we were able to export all the analysis information that we had into spreadsheets, okay? So that, and it looks at even used for design, spec checking, those types of things. But we have all of those nodes, elements defined, right? So what we need to do now is translate that to a physical model, what I call a physical model or BIM type model here, where we're starting to get a more accurate picture, not only just what we need for analysis, but what we need for accurate quantities, visualization, those types of efforts, even things like looking at vertical clearance. So in terms of what we need to do, we have the analysis model. We do not have vertical profile. If you're familiar with bridge analysis, typically we don't include the Z elevation within our models, right? That's typically ignored, but we need that for a physical model. So we need to add that through, we were able to pull in our profile information and add that to it so we have accurate not only X, Y coordinates, but Z coordinates as well. And in this particular case, we're able to add things like cross slope that again is typically not defined with that with the analysis model, but we're able to add that here by manipulating our spreadsheets before we get into our demonstration of using automation with PythonParts. So now that we have the information in our spreadsheets that is accurate and what we need for our physical model, we want to look at how we can efficiently create our model, right? Our nodes, some of those repeatable tasks, right? You saw how large that truss was. Do we want to make sure we're connecting every single node, every single beam, truss element to every gusset plate, right? And also, not only is that repeatable task, it's also very time consuming and tedious, right? So we want to take this information and be able to generate it now to a physical model that we can use for additional benefits, additional tasks afterward. So now I'm going to turn it over to Hanjin to discuss a little bit of background on PythonParts, what it is, what are some of the capabilities, but also look at specifically what was done in our particular case in order to generate this truss model.
I'm going to show you a demo of PythonParts. For this demo, I will create a truss model that contains two trusses. To define the PythonParts module, I need the following files: a py file for defining the truss model, a pyp file for defining the user interface, and some image files for decorating the icon and the user interface, and lastly, CSV files that contain the truss coordinates. The first two files are necessary for all the PythonParts modules, and the last two files are optional. I put the files in two places in order for all plan to use them. They are put in the folder where all plan was installed. The pyp files and the image files are used for the user interface. They've been put in the PythonParts folder under the library folder. I created a subfolder for my company and then put the files here. The py file and the CSV files are used for model generation. They are in the PythonParts scripts folder, and then the subfolder here. To browse to the PythonParts module I've created, I just need to follow the folder hierarchy for the PYP file. So in the all-plan user interface, I go to the library and PythonParts, and then Michael Baker International, and this is the module for the Truss. So double-click on it, and we will see the interface for the Truss input. The module interface is completely defined in the PYP file, which can be parsed by the all-plan software. Basically, PYP file is an XML file, which is pretty human readable. For example, the script node here defines the overall layout and the metadata. Here it defines where the related PY file is, and the name of the module, the version, and the width of the components of the interface. And the page node contains the detailed definition of all the components. For example, here it defines the image file, and similarly, I can define the drop-down list box and then the checkboxes. Let's take a closer look at the Truss input. So these inputs are largely based on the software-neutral data schema IFC. I use IFC because it's more convenient to exchange the data after I define the model. So the first drop-down list is about the object type. I chose the IFC member, and similarly, I can also choose, say, IFC beam, IFC column, etc. And then the subtype is for the type of truss. So this truss is a Warren truss. And here I can input a truss model name, and also the truss material, which is steel. And similarly, I can choose concrete and timber, and the name of the steel material, and also the shape of the member cross-section. So this drop-down list is pretty interesting. It's actually related to the drop-down list here. So for example, I choose road shape here. This list contains all the road shape, W shape. But if I choose the angle here, you see the list contains all the angle sections. And similarly for the T shape. And if I change the material from steel to concrete, and the other drop-down list also got changed. And if I use timber, now timber doesn't have a built-in cross-section, so we can just input the cross-section by ourselves. And down here, we can define the information regarding the all plan. So for example, the color of the truss model, and then the layer on which we can build a truss model. So after I input all the truss data, we can now generate the model. We can select which truss to generate. First, the upstream truss and its components, the upper chords, lower chords, and the diagonal members, and the downstream truss. And in this drop-down list, we can select what type of model we want to generate. There is the line model and the solid model. Let me choose the line model first. I click the Generate button and click on a plane area and then zoom in. Now I can see the model, the top view, elevation view, and the isometric view. So for line model, basically I just model the truss members as 3D lines. And let me toggle to the solid model. And as you can see, for the solid model, I define the truss members as solid objects. Basically, the object is based on the truss cross-section, and then I sweep the cross-section along the truss member length. And I can also switch on and off individual members. Say, turn off the lower chords or ignore the diagonal members. After I click the Generate button, what happened behind the scene is that the Python codes I've wrote retrieved the truss input I've selected and entered, and also the codes retrieved the truss coordinates from the CSV files. And then the codes call the the all-plan API functions to generate the truss models. So the process sounds pretty sophisticated, and you might think it's really hard to write Python codes, but actually it's not that bad, because all-plans provides a very detailed documentation to explain the concepts of using Python, and it also provides numerous PythonParts examples. And sometimes we can use some tools to write Python codes for us, such as ChatGPT. All we need to do is to write the requirements, such as write Python codes for getting data from CSV file. And ChatGPT can show us an example. And it not only shows us the codes, but also the explanation. Okay, now with this truss model, we can keep refining it within all-plan software, or we can export it into different data formats. And those formats can be read by various software. For example, we can export the truss model to a DWG file, which can be read by AutoCAD, or the DGN file, which can be read by MicroStation. So this is the truss model in AutoCAD. I just imported into AutoCAD. And the DWG file can also be read by the Midas software for analysis and design. And this is the truss model in MicroStation. Other than these two software, I can also export the truss model as the IFC data. So IFC is a very popular data schema. It's adopted by the considered as the de facto data schema for the US bridge industry. So all-plan supports many versions of IFC, such as the previous IFC 2.3 format, IFC 4, and the latest IFC 4.3 format.
Okay, thank you, Hanjin. So as Hanjin showed with those exports, we're going to talk a little bit about what we can do with that in terms of additional outputs and benefits with our model. So as Hanjin mentioned, one of our main opportunities here is to go directly to CAD programs. So we were able to bring this into the CAD software that was required by the client, fully using our automated model as the starting point now that we can continue to add detail, things like peers, additional members as needed, to provide that full visualization and quantity model, BIM model, if you will, within our ecosystem. From there, we're able to export that to more visualization software to look at, particularly in this case, using photorealism with shooting our model here in the background of real photos. We can also continue to develop that, and we did in this case with contextual information, creating a full 3D model of the surrounding area to be able to look at multiple outputs, multiple areas, multiple perspectives in terms of where we can find that information and look at this particular site. Here's one from barge traffic. Here's one from vehicle traffic. From there, we're in a CAD program, we can generate our drawing. So here's just a general plan elevation. Again, the only thing different here is that we're generating that directly from our 3D model started by our automation piece. Typical section as well, being able to generate that directly from our model. So just as a summary, wrapping up, we're able to quickly generate our accurate geometry, our different sections that we need based on our structural analysis, as well as material properties, being able to link that directly to our model, starting to create that BIM model. And as I mentioned, this is really the starting point. We're able to do that. We didn't take this and fully automate the piers, for example, or even the approach bands, because we had other applications, we had other ways of doing that much more efficiently than going through that process here. But we were able to still provide what we needed in terms of quantities, the basis for visualization, and our 2D drawings from that process. And then finally, just to leave you with this, that make sure you're looking at the return on investment. As I mentioned, we didn't automate the entire process for every element on this. We looked at what we needed to do, what was tedious, what was repeatable tasks, and what was the information that we had at hand that we could use to automate parts of this to make this process more efficient, better quality, and more effective. Thank you again for your time, and we hope you enjoyed our presentation.